Hello viewers, welcome to the session on data structures. In this video, we will see about the binary tree data structure, where we will discuss about binary tree ADT, its implementation, types of binary tree, and its property. Let us see what is binary tree. A binary tree is a special tree data structure in which each node can have at most 2 children. That is, no node can have more than 2 children. Thus, in a binary tree, each node has either 0 child or 1 child or 2 children. This is an example of the binary tree. You can observe that no node has more than 2 children. Let us see the formal definition of binary tree. A binary tree is a finite set of nodes that is either empty or consists of a root and two disjoint binary trees called the left subtree and the right subtree. Any tree can be transformed into a binary tree by left child and right sibling representation. Hope you have watched my previous video for left child right sibling representation. The tree shown here is the left child right sibling representation of the tree. Looking into the ADT of binary tree, the binary tree object is a collection of nodes in which every node except the leaf node have at most 2 children. The major operations performed in the binary tree are insertion and deletion. The insert operation will insert the node in the binary tree, whereas the deletion operation will remove the node from the binary tree. Other than this, we have search operation and tree traversal operation. Let us see the implementation of the binary tree. There are two ways of representing the binary tree. Either the array implementation, the other one is linked list implementation. Let us see representation in detail. In binary tree, each node is arranged from top to bottom and from left to right. The fact is that the maximum number of nodes in the binary tree of depth n is 2 power n minus 1. Hence, if we know the maximum depth of the tree, then we can represent the binary tree using the array data structure, where the array is declared with this maximum size as 2 power n minus 1. In the array, the elements are placed by using the formula. The root node is placed at the index 0 of the array. The left child of the node n is placed at index 2 into n plus 1. The right child of the node is placed at index 2 into n plus 2. The parent of the node will be at index floor of n minus 1 by 2. All the elements of the tree are placed in the array by applying these formulas. Let me demonstrate with an example. Consider the tree shown. As A is the root node, so it is placed at index 0. The node B is left child of A, so which is placed at index 1 by applying the formula 2 into n plus 1, where n is 0 as A is at index 0. The node C, which is the right child of node A, is placed at index 2 by applying the formula 2 into n plus 2, where n is 0 as A is at index 0. Similarly, the other nodes are located at index by applying the formula by which the node D is located at index 3, E at 4, F at 5 and G at 6. It seems to be as if the nodes are arranged sequentially in the array. It happens so as nodes are completely filled. Let us see the other example. Here the depth of the tree is 4. The maximum number of nodes the tree can have is 2 power 4 minus 1, which is 15. Hence, the maximum size of the array is declared as 15. In this tree, let us see where the nodes H, I, J are located in the array. The node H is located at index 7 as it is the left child of the node D, which is located at index 3. By applying the formula 2 into 3 plus 1. The node I is located at index A as it is the right child of node D, which is located at index 3. By applying the formula 2 into 3 plus 2. By applying the formula of the right child, we get the node J is located at index 12. As there is no left child or right child for node E and G, the corresponding left child and right child entries are blank. Here is the practice question. Find where the nodes J and K are placed in the array. Yes, you are right. The nodes J and K are placed at index 11 and 13 respectively by applying the formula. Next, let us see the binary tree implementation using list. Double linked list is used to represent a binary tree. In double linked list, every node consists of three fields. The first field for storing left child address, second for storing the actual data, and third for storing the right child address. The structure of tree node is declared as struct tree node, data of type int, left child pointer of type struct tree node, and right child pointer of type struct tree node. This is how the tree node looks like. Let us see the example. Here the root node is A. As B and C are left and right child of A, the left child pointer of A contains the address of node B, which is 1028, and the right child pointer of A contains the address of node C, which is 2024. Similarly, as B and E are left and right child of B, nodes B left child pointer contains the address of node G, which is 2804, and the right child pointer field contains the address of node E, which is 2048. You can observe how other nodes are linked. This is how the tree is implemented through the list representation. Now let us compare the array and the linked representation of the binary tree. The array representation makes use of the index, whereas the linked list representation, there is no index. The array representation requires less space to store the data, whereas linked list representation requires more space to store data due to the need of additional space for storing the pointers to left and the right subtrees. Next, the array representation requires prior knowledge of the depth of the tree to declare the array size, whereas the linked list representation requires no prior knowledge of the depth of the tree. Next, the direct access to any node is possible in the array representation, whereas that access is not possible in the linked list representation. Next, finding parent, left child or right child of a particular node is faster in the array representation because of the random access, whereas these operations are slow compared to the array representation in the linked list representation. Next, the major disadvantage is wastage of memory, especially in the case of skewed tree. Whereas in the linked list representation, the memory allocation is dynamic, so there is no wastage of memory. Next, the insertion and deletion of data is difficult in array representation, whereas these operations are easy in the linked list representation. Next, let us see the types of tree. There are 4 types of binary tree, which are full binary tree, perfect binary tree, complete binary tree, and skewed binary tree. Let us see about each type. That is, first, full binary tree. A binary tree in which every node has either 0 or 2 children is called as a full binary tree. It is also called as a strictly binary tree. The example tree shown here is of type full binary tree. Observe that each and every node has either 0 or 2 children. Next, the perfect binary tree. A binary tree is said to be a perfect binary tree when it satisfies the following 2 properties. Every internal node has exactly 2 children and all leaf nodes are at the same level. Observe the example. It is perfect binary tree as it satisfies both these properties. Next, the complete binary tree. A binary tree is said to be complete binary tree when it satisfies the following two properties. All the levels are completely filled except the last level. And the last level must be strictly filled from left to right. The tree shown here is an example of a complete binary tree. Observe here, the last level is filled from left to right and other levels are completely filled. The last type of tree is the skewed binary tree. A binary tree in which all nodes have only either one child or no child is a skewed binary tree. Tree shown here is an example of a skewed binary tree. Further, the skewed binary tree is classified as left skewed tree and right skewed tree. If a tree is dominated by the left child, then it is called left skewed tree, and if it is dominated by the right child, it is called the right skewed tree. Next, let us note down the properties of binary tree. A tree with n nodes has exactly n-1 number of edges. The maximum number of nodes in the binary tree of depth k is 2 power k minus 1, where k is greater than or equal to 1. Next property, the maximum number of nodes at any level I in a binary tree is 2 power I minus 1, where I is greater than or equal to 1. Next, the total number of leaf nodes in a binary tree is equal to the total number of nodes with 2 children plus 1. Next, we will see about the tree traversal in my next video. Hope you enjoy the video. Have a happy learning.